Given two circles and their diameters, we'll show that the ratio of circle areas is proportional to the ratio of their squared diameters. We'll use a proof by contradiction for this one, and first assume BD squared to FH squared is proportional to circle ABC to area S, where area S is less than circle EFG. Begin by inscribing a square in circle EFG. This square is greater than half the circle. This is seen by circumscribing the circle with another square. The inscribed square is equal to half the circumscribed square, as you can see, which is greater than the circle, so the inscribed square is certainly greater than half the circle. We use the inscribed square to cut the circle into 4 segments. Since the inscribed square is greater than half the circle, the 4 segments are less than half the circle. Let's take it a step further by constructing this octagon. Focus on this segment of the circle left over by the square. If we construct this parallelogram as so, the triangle made by the octagon and square is equal to half the parallelogram, as easily seen. The parallelogram is bigger than the circle segment, so the triangle is greater than half the circle segment. Proposition 10.1 shows that if we continue this process, we'll eventually arrive at an inscribed polygon as close in size to the circle as we please, but always less than it. This means we'll eventually arrive at a polygon greater than area S, but less than the circle. For the sake of the argument, we'll assume we did that with the octagon. Now construct an octagon inscribed in circle ABC, similar to our octagon in circle EFG. Then the previous proposition says BD squared to FH squared is proportional to the octagon ABC to the octagon EFG. But by assumption, BD squared to FH squared is proportional to circle ABC to the area S. So, circle ABC to the area S is proportional to the octagon ABC to the octagon EFG, or that the circle ABC to the octagon ABC is proportional to the area S to the octagon EFG. Circle ABC is greater than octagon ABC, so area S is greater than octagon EFG. But it should also be less than it, so there's our contradiction. We can similarly show that circle EFG to area S is not proportional to FH squared to BD squared, where area S is less than circle ABC. We'll now assume that circle ABC to area S is proportional to BD squared to FH squared, where area S is greater than circle EFG. Then FH squared to BD squared is proportional to area S to circle ABC. We'll show in the lemma that follows this proposition that the area S to circle ABC is proportional to circle EFG to area T, where area T is less than circle ABC, which we just showed is impossible, so there's our contradiction, so area S is equal to circle EFG, and BD squared to FH squared is proportional to circle ABC to circle EFG.